We all know, like the standard textbook model of physical exhaustion, right? You go to the gym, you do a heavy set of bicep curls, your arm runs out of ATP, lactic acid builds up, and eventually that specific arm is just completely toast.
Right, yeah. It's treated as a very localized event.
Exactly, like treating the human body as just this collection of isolated engines.
Yeah, the assumption there is that the fuel tank in your left arm has absolutely nothing to do with the fuel tank in your right arm.
But then, if you start looking at the actual neurology of fatigue, that whole isolated engine model completely breaks down.
Oh, totally. It falls apart.
Picture this scenario for a second. You decide to exhaust your right leg by hopping on it relentlessly, like as fast and as hard as you can.
Just burning it out.
Right. And your left leg has been doing absolutely nothing. It's just hovering there, completely rested.
Not a single muscle fiber firing.
Exactly. Yet when you finally stop and try to jump with that left leg, it's suddenly, like, measurably weaker. The power is just gone.
Which is wild, right? Because it did zero work.
Zero. And here is the real paradox.
Mm-hmm.
If you drop down to the floor in that exact same moment to do a push-up, your arms are perfectly strong.
Yeah, so the fatigue effectively jumps across your body to a rested limb, but it selectively ignores your upper body entirely.
It makes no sense at first glance. So, to figure out why our bodies pull this bizarre neurological trick, we are doing a deep dive into a brilliant 2026 paper published in the Journal of Sports Science and Medicine.
It's such a good paper.
It really is. The authors are Mahta, Sardroodian, Hiwa, Rahmani, and David G. Behm. And the title alone gives away the entire plot of today's discussion. It's called Dominant Leg Continuous Unilateral Hopping Impairs Contralateral Leg, but not Upper Body Explosive Performance.
A very literal title.
Very literal. But let's break down exactly what they discovered, because they found a way to essentially hack the nervous system using nothing but like a 10-second pause.
Yeah, and the beauty of this specific study is how rigorously it tests this crossover fatigue effect using explosive dynamic movement. It moves away from the older methods of just, testing static muscle holds, and it forces us to look at how the brain manages complex locomotion under extreme stress.
Okay, but before we can even begin to understand why the fatigue crosses over to a totally rested left leg, we need to establish the baseline of what they were actually testing here.
Right, the mechanisms.
We have to separate peripheral fatigue from central fatigue, because we know peripheral fatigue pretty well.
Yeah, that's the muscle itself mechanically failing.
Right, the local energy sources are depleted, metabolites are swimming around in the tissue, and the muscle fibers physically just cannot produce force.
The physical hardware is basically breaking down at the exact site of the exercise.
If we use a car analogy, peripheral fatigue is the engine literally sputtering out of gas.
Right.
That specific motor physically cannot keep turning over. But this study is hunting for central fatigue, which originates in the nervous system, like the brain and the spinal cord.
Yeah, the software, not the hardware.
Exactly. I'm trying to think of how that fits the car analogy. I guess it would be more like a modern vehicle with a digital internal computer system.
Oh, I like that.
Right.
Yeah.
Like if the engine starts getting too hot, the central computer kicks in and artificially caps your top speed at 20 miles an hour.
Yeah, exactly. The engine might still have gas, the tires are completely fine, but the central computer is saying, nope, we are throttling the system to prevent catastrophic damage.
The computer just overrides everything.
Right, so the central nervous system is actively reducing its capacity, or its willingness, really, to send the electrical drive down to the muscle.
And for decades, physiologists have debated a pretty crucial question about this.
Yeah, when that central computer dials back the drive, does it throttle the entire human body uniformly, or does it only throttle specific circuits?
Which brings us to the methodology. To test this, the research team brought in 18 healthy adults. I think it was 13 males and 5 females.
Yeah, mostly in their late 20s and 30s. And they put them through an incredibly demanding protocol.
Demanding is an understatement. If you have ever tried to hop on one leg for a full minute, aiming for maximum height and minimal ground contact time, it is just pure localized torture.
It's awful.
They call this the continuous fatigue protocol. 1 straight minute of explosive unilateral hopping on their dominant leg.
And then, to create a point of comparison, they had those exact same participants come back on a different day to perform an intermittent fatigue protocol.
Okay, how is that different?
Well, the total workload was identical. They still did 60 seconds of maximum effort hopping on the dominant leg, but this time it was broken into 2 30-second bouts. separated by a microscopic 10-second rest.
Just 10 seconds.
Just 10 seconds.
Wow. We're definitely going to come back to that 10-second pause because the physiological impact it had is just staggering.
It really is.
So they completely exhaust the dominant leg. But the genius of the methodology here is that they didn't actually care about the dominant leg.
Right, they wanted to test the rested systems.
Exactly. They tested the non-dominant leg, the one that had been doing absolutely nothing, and they tested the upper body.
And measuring performance in these rested limbs required some very specific metrics. For the non-dominant leg, they had the participants perform 10 rapid, explosive unilateral hops.
Testing the fresh leg.
Right. They were measuring hop height, overall lower limb power, and something called the Reactive Strength Index, or RSI.
The reactive strength index is like a fascinating metric on its own.
Oh, for sure.
It's basically your flight time divided by your ground contact time. It measures how effectively you are utilizing the stretch-shortening cycle in your tendons.
It tells you how springy you are.
Yeah, exactly. If your nervous system is firing optimally, you hit the ground and bounce back up instantly like a stiff rubber ball.
And if your nervous system is lagging...
You sink into the ground, your contact time increases, and you just lose all that elastic energy.
Right. So alongside the hops, they tested the upper body by having the participants perform 5 explosive rebound push-ups.
Rebound push-ups, so that's...
where you drop from a kneeling position, hit the floor, and immediately explode back up, pushing your hands off the ground.
Got it.
Yeah. And they measured all of this performance before the fatiguing exercise started, and then tested everything again at 1 minute, 5 minutes, and 10 minutes post-exercise.
They were actively looking for that crossover effect.
Yeah.
They wanted to see if the central computer was penalizing the rested hardware.
And the asymmetrical response of the human body here is just wild.
Let's look at the primary findings from that continuous 1-minute non-stop hopping protocol first.
Okay.
When they tested the rested non-dominant leg just 1 minute after the exercise, its performance completely fell off a cliff.
The data showed massive, statistically significant drops across the board.
Yeah.
The rested leg lost hop height, it lost overall lower limb power, and that reactive strength index just plummeted.
So the tendons were no longer acting like stiff rubber balls.
Exactly. The neuromuscular timing was completely sluggish.
And the impairment lasted for quite a while too, didn't it?
It did. At the 5-minute mark post-exercise, that non-dominant leg was still showing significantly lower hop height and lower overall power compared to the pre-test baseline.
So it took a full 10 minutes for that rested leg to finally recover its baseline explosive performance.
Yep. 10 minutes.
That's crazy. I am hopping on my right leg until it burns. My left leg is literally just resting. Yet for the next 5 minutes, my left leg is demonstrably weaker.
But then we look at the upper body.
Right, those 5 explosive rebound push-ups. The arms were just as explosive at 1 minute post-exercise as they were before the leg hopping even started.
The upper body explosive performance was completely untouched by the exhaustion occurring in the lower body.
Okay, let's unpack this. Because this is where I have to question the biological logic of our bodies.
Sure.
If the central nervous system is fatigued, if the brain is recognizing a massive stress event and putting the brakes on the system to protect it, why wouldn't it just shut everything down uniformly?
You'd think it would, right?
Yeah. Why on earth does the brain heavily penalize the left leg, but give the arms a total free pass?
What's fascinating here is that it comes down to how our neural wiring is compartmentalized in the spinal cord.
Okay.
Neurologists differentiate between homologous muscle groups and heterologous muscle groups.
Homologous meaning?
Homologous refers to the exact same muscle group on the opposite side of the body. So your right calf and your left calf. Your right quad and your left quad.
Right, that makes sense.
These homologous pairs share an incredibly strong neural coupling. They operate at the exact same vertebral spinal level.
Oh, I see. It feels like having separate breaker boxes in a house.
Yes. Perfect analogy.
Like you plug 3 space heaters into the living room outlets, and that specific breaker trips. The power goes out in the living room, and maybe the hallway that shares that same local circuit.
Which would be your other leg in this scenario.
Right, but the kitchen, which is wired to a totally different breaker down the basement, just keeps running perfectly fine.
And that's your upper body. The breaker box concept captures the structural reality perfectly. When you exhaust the dominant leg, the peripheral fatigue, the actual metabolic waste, the hydrogen ions, the muscle fiber failure, that stays strictly confined to the right leg.
Because the left leg's tissue is pristine.
Exactly. But the sensory signals sent back up to the central nervous system affect the entire spinal level responsible for the lower limbs.
So the brain essentially receives an alert, that the lower quadrant is under extreme distress and it just, like, turns down the master dial on the entire lower quadrant.
From an evolutionary standpoint, it is a brilliant failsafe.
How so?
Think about it. If your right leg is failing during an intense physical exertion, say you're sprinting away from a threat or climbing, your spinal cord assumes the entire lower half locomotion system is entering a critical failure mode.
All right.
It downregulates the whole lumbar circuit to prevent you from catastrophically tearing a muscle or pushing the system to absolute ruin.
But the arms are heterologous.
Right. They are anatomically distant muscle groups, controlled by completely different higher segments of the spinal cord.
So the data here essentially confirms that those distant upper body neural networks are distinct enough that the central fatigue from the legs simply doesn't cross that barrier.
Exactly.
This highly targeted inhibition based on neural proximity leads us directly into the deeply mechanistic side of things.
Neurobiology.
Yeah, like how does the muscle actually communicate this distress to the brain? The researchers point out that you can manipulate this crossover fatigue by tweaking just one tiny variable.
Which brings us to those group 3 and group 3 afferents.
Right. We have to look at the biological alarm system embedded in our tissue.
Yeah, during that sustained 1-minute continuous hopping, the working muscle is building up an immense amount of metabolic byproducts.
And inside the muscle casing, you have these sensory nerve fibers, right? The group 3 and group 4 afferents.
Yes. Group 3 afferents are primarily mechanoreceptors. They sense physical pressure, tension, the literal mechanical strain of the muscle tissue stretching and contracting.
And the group 4V afferents are the chemoreceptors, right?
Spot on.
They're essentially tasting the internal environment of the muscle.
Yeah.
They are sensing the drop in oxygen, the rising acidity, the buildup of potassium and lactic acid.
They are monitoring the chemical degradation in real time.
Wow.
And as the continuous hopping pushes past the 30-second mark, these afferents start firing wildly.
Just freaking out.
Literally, they send massive, continuous streams of feedback up the spinal cord to the brain, essentially screaming that the local environment is becoming toxic and mechanical failure is imminent.
So the brain receives this screaming afferent feedback and responds by depressing the central motor drive.
Yes, it actively reduces the voluntary electrical activation it sends back down to the muscles.
And because of that homologous neural coupling, it doesn't just reduce the drive to the working right leg, it cuts the power to the left leg too.
Which brings us back to the intermittent protocol.
Ah, yes. The 10-second rest.
Right. They hop for 30 seconds, took a 10-second rest, and hop for 30 more seconds.
So the total work is identical. Now, I would assume that a 10-second pause is nowhere near enough time for the circulatory system to flush out all that acid and potassium.
Do you think not?
The peripheral plumbing is still backed up, so the crossover fatigue must have still been there, right?
Yeah. That assumption makes perfect sense if we were only dealing with localized peripheral plumbing. But the findings prove the exact opposite.
Hey, really?
Yeah. When the researchers tested the rested non-dominant leg 1 minute after the intermittent protocol, the contralateral impairment had entirely vanished.
Are you serious?
There was no significant loss of hop height, no loss of RSI, and no loss of power.
Wait, a 10-second pause completely prevented the crossover fatigue. The rested leg maintained 100% of its power just because the dominant leg got a 10-second break.
If we connect this to the bigger picture, it reveals just how rapidly adapting and dynamic our nervous system truly is.
That is insane.
That brief 10-second recovery interval allowed the local muscle to clear just enough metabolites, perhaps neutralizing just a fraction of the acidity, or restoring a tiny bit of oxygen, which was enough to quiet down those group 3 and group 4 afferents.
So the alarm system stopped screaming, even if just for a moment.
Exactly. And that momentary silence allowed the central nervous system to clear the inhibitory signals and preserve the central motor drive.
The brain is incredibly efficient at clearing out the protective inhibition if you just give it a tiny window of silence.
It really is.
That is such a practical hack for anyone doing unilateral training. But diving into the data, there is a massive contradiction regarding the RPE, right? The rating of perceived exertion.
Oh yeah, this is a great point. They asked the participants subjectively how hard the protocols felt.
And the results for perceived exertion showcase a fascinating disconnect between the mind and the muscle, particularly during the upper body testing, because the intermittent protocol saved the left leg's physical power. But when they asked the participants how exhausted they felt after doing the upper body rebound push-ups at the 1-minute post-exercise mark, The participants actually reported a much higher perception of effort following the intermittent protocol compared to the continuous one.
Which is so weird because the objective data, the flight time of the push-ups, the actual force produced, showed zero impairment.
Right.
Their arms were performing flawlessly. But subjectively, they felt significantly more exhausted in their upper body after the protocol that actually gave them a rest break.
This is wild. If our brains trick us into feeling globally tired when only a local circuit is strained, how much of our daily exhaustion is just like a neurological illusion?
A lot of it, probably.
You feel like you can't push any harder, you feel completely drained, but structurally, the heterologous muscles are totally fine. Why did the protocol with a rest break make them feel worse?
It highlights the complex difference between physical output and central arousal.
Okay, explain that.
Well, the sensation of fatigue is not just a readout of muscle capacity. It is a composite feeling created by cardiovascular strain, breathing rate, and psychological load.
Right.
The start and stop nature of the intermittent protocol requires you to push to the limit, stop, feel the blood pool and the heart rate spike during that 10 seconds, and then psychologically force yourself to initiate a second maximal bout.
Oh, that makes sense. That places a massive psychological and cardiovascular demand on the system.
Exactly. You feel globally exhausted. Your RPE skyrockets. But the actual central motor drive to the arms remains completely intact.
So feeling exhausted simply does not mean your muscles are actually incapable of producing explosive force.
Not at all.
The feeling of fatigue and the reality of fatigue are two totally different data streams.
Yeah.
And this actually forces a question about the history of sports science. If this brain drain effect, this homologous crossover, is such a fundamental biological response, why haven't we noticed it earlier?
Have researchers just been missing this for decades?
Yeah, why is this a 2026 paper?
Well, the crossover effect has been notoriously elusive in the literature, and it really comes down to task specificity.
Task specificity.
Yeah. A lot of prior non-local muscle fatigue studies intervened with isometric contractions.
Well, like holding a pose.
Right. They would have participants hold a static leg extension or push constantly against an immovable wall. It is a slow, sustained, grinding burn.
Okay.
And when researchers tested contralateral fatigue after those static holds, the results were all over the place. Sometimes the rested limb showed weakness, often it didn't.
Because a static wall sit doesn't tax the brain's software the same way a plyometric jump does.
Precisely. Explosive movements like unilateral hopping require highly complex, multi-joint central motor control.
You need rapid force development.
You need precise neuromuscular timing to utilize the stretch shortening cycle, and you need your core musculature firing rapidly to stabilize your posture in midair.
So an explosive task requires an immense amount of integration and processing power from the central nervous system.
Exactly. The brain is processing vastly more data during a jump than during a static hold.
Okay, so when the brain gets a little fatigued from the afferent feedback, it drops the highly complex tasks first.
Yeah.
It shows up immediately in a complex task like hopping on the other leg, but it wouldn't show up if you just asked the participant to do a slow, static hold on that other leg.
Exactly. The central fatigue is totally task-specific.
Dynamic high-velocity tasks are much more likely to reveal that the central computer is dialing back its processing power.
The neurological demand of the movement dictates whether the central fatigue will actually manifest physically.
Man, we have covered a massive amount of neurobiology here.
We really have.
We've explored how peripheral muscle burn triggers a cascade of sensory alarms, how the spinal cord selectively punishes homologous muscles to protect the system, but leaves the upper body untouched.
And how the brain prioritizes complex movements over static ones.
Right. Let's synthesize this dense neurological data into a practical framework for you listening right now.
I'd say the overarching takeaway is that fatigue is not merely a localized mechanical failure of tissue.
No, it's not.
It is a highly protective mechanism, deeply mediated by the brain and spinal cord. If you continuously exhaust one limb, your brain will temporarily limit the explosive capacity of the corresponding homologous limb on the other side of your body.
So your completely rested left leg will suffer simply because your right leg was screaming at your brain.
Right.
But importantly, your upper body is operating on a different neural circuit. It remains completely untouched by that lower body distress.
And perhaps the most actionable takeaway, you can hack this biological failsafe.
The 10-second rule.
Yes. Brief rests, Literally just 10 seconds of pausing can clear the accumulated metabolites just enough to silence the sensory alarms.
Break the cycle of inhibitory feedback.
Exactly, and fully restore that central drive. Fatigue is as much an illusion created by the brain to protect you as it is a physical reality in the muscle.
Recognizing this totally changes how we approach physical limits.
It does. The absolute limitation isn't always residing in the muscle tissue. More often than not, the limitation is in the signal being sent from the brain.
Which leaves us with a final provocative thought for you to ponder.
Okay, what is it?
The next time you are in the gym, on a run, or attempting any grueling physical task, and you feel that overwhelming wave of complete exhaustion hit you, ask yourself, is your muscle actually failing?
Oh, I like that.
Or is your brain's central motor drive just experiencing a temporary protective inhibition? Could a mere 10-second pause completely reset your nervous system, clear the alarms, and unlock power you didn't know you still had?
The feeling of hitting a wall might just be a suggestion from your nervous system, not a structural reality.
Exactly. Questioning the origin of your fatigue is a powerful tool when you are trying to push your boundaries. The diagnostic landscape of physical exhaustion is incredibly murky, and your brain is pulling the strings behind the scenes in ways we are only just beginning to map out.
We highly encourage you to read the full article by Sardroodian, Rahmani, and Behm in the Journal of Sports Science and Medicine to explore the raw data and methodology for yourself.
Seriously, the charts breaking down the reactive strength index and the timeline of recovery are absolutely fascinating, and they add so much visual context to this discussion.
The granular detail in their methodology really sets a new standard for how we measure central fatigue in dynamic movements.
Be sure to follow the channel and turn on notifications so you never miss out on our next deep dive into scientifically rigorous content like this. Until next time, keep questioning what your body is actually telling you.